All right, so a very classic problem in AP Physics 1, AP Physics C is just the block on a ramp, right? So if you have a block on a ramp of a certain angle of inclination, you can pretty easily find the acceleration of this block, right? It's just about reorienting your axis. If you reorient your axis so that the x direction is parallel to the ramp, y direction is perpendicular to the ramp, you can find that the acceleration is equal to g sine theta, or g sine phi, whatever. 9.8 times whatever your the sine of that angle of inclination. And that is found by reorienting the axis. But one of the beautiful things about physics is that it's governed by nature, right? Like this trick of reorienting the axis, that's like a trick that humans kind of came up with. But regardless of how you get to your result, the acceleration will equal g sine phi or theta, whatever. I'll just make it theta. I don't know why I drew a phi. Point is, the acceleration is going to equal g sine theta no matter what, and regardless of how you got to that result. So I'm going to be showing you how to get the acceleration of a block on a ramp using just your normal like y-x axis, right? Like no reorienting the axis, just doing it like this. And when you do it like that, when you draw your FBD, so let's get I drew kind of that weight vector, but when you draw your FBD in this kind of a scenario, now instead of splitting FG's components, you're going to be splitting Fn into different components. So Fn x, Fn, this will be y, right? And then Fn y. Both of these vectors together are their components of the Fn vector. So I can make that a little bit more clear. There's, because you have a net force in kind of two directions, right? You have an unbalanced force in the y direction and unbalanced forces in the x direction. So you're going to have acceleration with components in both the x and y direction. So to find the magnitude of that acceleration, we can use, right, a squared is going to equal ax squared plus ay squared, right? Finding the magnitude of a vector. And like that, we can kind of just start solving in using our Fnet equations, right, for acceleration. So Fnet in the x direction equals max, which is going to equal Fnx. Now, if you think about, so if this was our Fg, and this was our Fn, then this angle right here would be 90 minus theta. And then if you had this right here, right, your Fnx, or y and Fnx, then you can use some geometry to show that this angle right here would be theta, right? Because if this is 90 minus theta, then if you think about this, making a line like so, this angle right here is 90 minus theta. So then this angle has to be 90 minus theta. And then this whole thing is a right angle, you get theta. So this is going to be, if this angle right here is theta, the x component is sine theta. And then same thing for Fnet y, you get may is going to equal Fg minus Fny, which is just cosine theta. So now we can substitute everything in for acceleration into like our magnitude of the vector equation. So it's going to equal ax squared. Well, this is just Fn sine theta. Fn sine theta over m squared plus Fg minus Fn cosine theta squared. Sine theta over m squared, I should say. So, when you square, you're squaring, right, the numerator and denominator. In the denominator, they're both going to have a 1 over m squared in them. So I can just factor that out already, just for foreseeing that. And what you really get is going to be Fn squared, right, when you start squaring everything. Fn squared sine squared theta plus Fg squared you're squaring a binomial, right? So you're going to have that minus 2fg fn, which is kind of funky. 2fg fn cosine theta plus fn squared, cosine squared. Sorry, I wrote something else. Cosine squared theta. When you factor out that, or when you multiply out that whole binomial. So this whole thing right here is just fg minus fn cosine theta squared, right? So 1 over m squared. Now, what you might notice already is you have this fn squared sine squared theta, and this fn squared cosine squared theta. And if you were to take those two terms, group them together, and then factor out that fn squared, you get sine squared theta plus cosine squared theta. And let me also just get the fg minus 2fg fn cosine theta right here. And hopefully this is a familiar identity, maybe not if you're in AP Physics 1, but if you're in C, you're probably familiar. This is the Pythagorean identity. So this whole thing ends up just equaling 1. So in short, now we're left with fg squared, I forgot the squared there, my fault, fg squared minus 2fg fn cosine theta plus fn squared. So we're missing, essentially, like, we need to know what fn is in terms of g and theta, right? Like, in our acceleration equation, it won't be in terms of the normal force. We have to show that the normal force is going to be in terms of g and theta, right? And in the old way of reorienting the axis, that's pretty simple, because you know that fn is just going to equal fg cosine theta, right? When you reorient your axis, fn equals fgy. But we're not reorienting the axis, so we can't just, substitute that in if this is going to be at least somewhat of a formal proof. We have to show that, fn is in terms of g and theta and stuff. So the way you can really go about doing it is, you can imagine it starting at the top, or if you just started at this, or if the block starts sliding at this moment right here, then in the same amount of time, by the time it hits the point, in that time interval, it will have traveled a vertical distance h and a horizontal distance x. And so this would also be x right here. And because this is a right triangle, we can express x and h as tan theta. So tan theta equals h over x, right? So if we have h over x, then we can use kinematics to kind of substitute in h and x. Remember, for our displacement equation, change in x equals 1/2 at squared plus v naught times time. We will discard the v naught because we can say that the block initially starts with the speed 0. We just got to make this equation work for both directions, the y direction and the x direction. So you get tan theta is going to equal 1/2 ax, or ay, t squared, over 1/2 ax, t squared. And we can start then substituting in, right, the actual equations for acceleration. So fn, fg minus fn, cosine theta over mt squared over 1/2 fn sine theta over mt squared. And what you notice is that the 1/2s and the t squared, they both cancel out, right? Because 1/2 is a constant, and then whatever time it takes to travel from top to bottom, like, that is the time it spends, right, traveling that distance x, as well as that height h. So it's the same time for travel in both directions, right? Time is the thing that connects the x and y motion. So really, and then when you drop the t's in the 1/2, you can think about more what this tan theta equation is saying in terms of vectors. But we can just from here solve for fn, because we can also drop the m's, right? The m's will drop because same mass. So we could say that fn sine theta times, so if I multiply the Fn sine theta to both sides, Fn sine theta times tan theta is going to equal Fg minus Fn cosine theta. And now we can add the Fn to both sides, and then we will end up factoring out the Fn. Once we've added Fn cosine theta to both sides, it's really the same as Fn times sine theta tan theta plus cosine theta, which is a mouthful. But what you will soon realize is that sine theta times tan theta, that is the same, right? Remember, tan is sine over cosine. So sine times sine is sine squared. So you get sine squared over cosine, cosine theta. And then we'll have cosine theta. And, you know, this is a fraction, and we're trying to add cosine theta to it. We got to make sure that it has the same, I forget what you call it, like least common denominator. Like it needs the same denominator in order to add. So if this is cosine theta over 1, then we can multiply the top and bottom of that, you know, cosine theta over 1 with just cosine theta. And that will get us cosine squared theta over cosine theta is going to equal Fg. Which, when we're adding fractions, I wrote an Fg here, my fault. When we're adding fractions, you leave the denominator alone because you're kind of adding, think about pizza, right? 4/3, or I guess 5/8 plus 2/8 is 7/8. Think about your pizza slices. Sine squared theta plus cosine squared theta, that's just 1, right? So I guess I might have went a little too fast here. I'm doing sine squared theta plus cosine squared theta over cosine squared theta. But that is just equal to 1, right? By Pythagorean identity. So now I can kind of show that, hey, Fn is indeed, if I multiply cosine theta to both sides, Fn is indeed equal to Fg cosine theta. And I can bring that in to our acceleration equation, right? So 1 over m squared, so Fg squared, minus 2Fg, Fn is just Fg cosine theta. So I'm doing times Fg cosine theta, right, for Fn, multiplied by cosine theta again, right, because this Fn just got replaced. And then plus Fn squared, that's just Fg squared times cosine squared theta. All right, now what can we do? Well, this here is the same as Fg squared, that Fg times Fg. Same thing here, cosine theta times cosine theta squared. Wait, cosine theta times cosine theta is just cosine squared theta, right? So now I can actually factor out Fg from this whole group. So I can pull Fg squared out. So Fg squared over m times m squared, times, so factoring that out, you get 1 minus 2 cosine squared theta plus cosine squared theta. So that is the same as, and first of all, now we can say Fg squared is just m squared g squared, right? And Fg equals mg. So 1 minus, now this will just end up, so if I take negative 2 times cosine squared theta, add on cosine squared theta, I just get left with minus cosine squared theta. And by, I think this is the third time using Pythagorean identity, this is just the same as sine squared theta. So the m squareds drop out, and I get g squared times sine squared theta. Or acceleration, when I take the square root of both sides, because I had acceleration squared at the top, acceleration is going to equal g sine theta. So pretty crazy process for a result that's so simple, and you learn it kind of in your first month of introductory physics class. But yeah, it's pretty crazy, right? You don't have to reorient your axis to get this result. Thank you for watching.